Well, hello, hello, howdy people. How's everybody doing today? All right, so today we are gonna do, this is gonna be PH 102, chapter 16, which is gonna be waves. So make sure to go on module, and here's a PowerPoint. All right, it's over here. All right, so waves. Now, when we talk about wave, what's a wave? So a wave is a periodic disturbance that move away from the source and carry energy and information with it. So supposedly, let's say, I don't know, I got a rope right over here, and I'm saying over here. So if I take that rope, the end of that rope, and put it up there, and I guess move it to the top, so you're gonna have that rope going something like this. And then we go back up. And then when you go out from the bottom, you're gonna get another wave when you actually get the rope and actually move it. It's gonna look like some of this. So if you actually take one of those waves and let's say you oscillate it. So basically you're gonna go back and forth, same thing with the, you do it from the bottom, you're gonna go back and forth, back and forth. So let's say you take one of these. So if you actually take a wave, so you're gonna have, I guess let's just take it from over the bottom. So it's going to look like something like this. So the distance from one end of the wave to the other end of the wave, from crest to crest or end to end, that's what we're going to be calling our lambda. That's going to be your wavelength. And that's going to be the distance from one end to another. Actually, let me actually redraw it. Let me draw a better wave. So let's say this is our wall over here. And you get this line coming in. All right, so if you take, I don't know, let's say we have a wave going in. Let me just go in all the way down. Okay, now, the distance from the middle line over here to the top, that's what we call your amplitude. Well, actually right over here, amplitude. So your distance from over here to the top, or actually you can go to the bottom, that's your amplitude. Your distance from crest to crest, that's your lambda, or from beginning to beginning. Let me actually get a different color for the lambda. So you can actually go from here to here. That's lambda, or you can go from crest to crest. That's also your wavelength, lambda. Now the bottom, this is called the trough. Now, so this is what we call a periodic wave. So the top is the amplitude, the distance from crest to crest, that's your wavelength, and then your bottom, that's your trough. Now, we need to talk about the rate that's going. So you might have a question of how many seconds for each cycle. And that's where we talk about the period, which we give it a big letter T. So your period is how many seconds for each cycle. So basically it's how many seconds per cycle. 30 seconds per cycle, 60 seconds per cycle, etc. All right, well, let's say if we have a question, let's say we have a question that says, all right, well, what is how many cycles you have per second? And that's when we talk about the frequency. So your frequency, F, let me just write this down, is your cycles per second, which is the opposite of seconds per cycle, which is the opposite of the period. So it's going to equal to 1 over the period. So your period is going to equal to 1 over F, and then your F, your frequency, also is going to equal to 1 over the period. So let's say, for instance, we say that we have a frequency of 10 hertz. By the way, I totally forgot to mention that. So cycles per second. Actually, let me just. The cycles per second, that's what we call, let me actually rewrite this down. The hertz, which is 1 over T. So your unit for frequency is your hertz. Now let's say if your frequency was 10 hertz, that means your period is going to equal to 1 over 10 seconds per cycle. So now, when we talk about wavelengths, we're talking about how far does the wave travel after one period. Or one cycle. Again, that's your wavelength, which is your lambda. Now, the distance, okay, so you got a wave, right? So your wave coming in here and is actually moving. Because it's moving, that means it has a velocity. Now, your velocity is going to equal to, which is your normal velocity definition, your distance over your time. In our case, your distance, that's your wavelength, over your time, which is your period. So this is going to be lambda over T, which actually you can say is lambda multiplied by 1 over T. Now, 1 over T, again, that's your frequency. Actually, let me just define this. Let me write this better. So this makes it lambda multiplied by your frequency. All right. Well, let's look over here. So your wave is a periodic disturbance that move away from the source and carry energy and information as it goes. Now, there's two types of waves. The two most important categories of waves are your mechanical waves and you get your electromagnetic waves. Your mechanical waves, which travel only through matter and involve the motion particles of the matter they pass through, for example, are sound waves. Your electromagnetic waves consist of varying electromagnetic field and can travel through a vacuum and through matter. We're going to see this later. Now, they don't involve motion particles of the matter they pass through, like light, wave, radio waves, and X-ray waves are some of the examples. Now, your transverse waves are mechanical waves in which a particle of the matter through which they pass move perpendicular to the wave direction. Transverse wave can only travel through solids. That means it's kind of like our little example. When you actually have a wave, it's going to be perpendicular to the wave direction. So as your wave direction is going to be perpendicular to it. Now, the other type of wave is your longitudinal wave, which is a mechanical wave in which the particles of matter through which they pass move parallel to the wave direction. It's kind of like if you have a slinky and you put it back and forth. So this is going parallel to the wave direction. So that's a longitudinal wave. Again, this is a good example actually from the transverse wave that we just tried to draw over here. Now, your wave amplitude, we defined it as the maximum displacement from the normal position of the particle of the medium through which the wave passes. Now, your wavelength is the distance from crest to crest or trough to trough. And again, trough is the bottom of the wave that we just showed on the drawing that we just did. So let's go ahead and look at this little video that we have. So if you go to modules, I'll put you all a little video. That's the first one.
The first segment of this animation shows a continuous transverse wave. The amplitude of the wave and the wavelength are both noted on the figure. The frequency is the rate at which the wave oscillates up and down. According to the wave equation, as the frequency of the wave increases, the wavelength decreases, if the speed of the wave is held constant.
So that's a transverse wave showing you the period and the frequency that is associated with it. Now, here's the other video.
Standing wave pattern. The animation shows a standing wave pattern in a rope.
Yeah, notice the nodes over here, there's no motion.
For the standing wave pattern is that both ends are nodes. Points on the rope that show no amplitude change and are called nodes. Points exactly halfway between the nodes display the greatest amplitude change and are called antinodes. The fundamental frequency and wavelength and the next two possible standing wave patterns and their frequencies are illustrated in the animation.
Wonderful. So your wave frequency is the number of crests that pass a given point each second. Now the unit of the frequency is your cycle per second, which we call hertz. Now the speed at which the rate moves from crest to crest equals to your frequency multiplied by lambda. We just showed that a little while ago. So it'd be the speed is going to equal to the frequency multiplied by the wavelength. So let's say we have a question. If 10 waves 2 meters long pass by each second, what is the wave speed? So let's do this example. So you got 10 waves. So your frequency is 10 hertz. Each are 2 meters long. So your lambda is 2 meters long. And you're looking for your speed. And knowing that the speed equals lambda multiplied by the frequency. So that's going to be equal to 10 for your frequency multiplied by lambda 2. So it's 20 meters per second. Awesome. Now, we mentioned that the period also is the time needed for the wave to go past a given point. So your period, again, equals 1 over f. So let's say we have another example. We do another example. Let's say in this example, we have a wavelength of 50 meters and a speed of 8.5. What is the frequency and the period? So for this one, what you get? Your lambda is 50 meters and your speed is 8.5 meters per second. You need to find the frequency and you need to find the period. Well, the frequency, actually not the frequency, the velocity equals lambda multiplied by the frequency. That means your frequency equals v divided by lambda, which is going to equal to, according to us, 8.5 divided by your 50. So it should be 0.17 hertz. Now your period is going to equal to 1 over the frequency, which is going to equal to 1 over 0.17. So let me just plug it in. 5.9 seconds. Excellent. Let's do one more example, shall we? Let's do another example. Let's say, here's another example. Let's say the velocity was 100 meters per second and your frequency was 20 hertz. Find the wavelength and find the period. Well, again, your V equals lambda F. That means your wavelength at this time is going to equal to your V divided by your frequency. So it's going to equal to 100 divided by 20, which is going to equal to 5 meters per second. For your period, which is going to be 1 over 20, 1 over the frequency. Actually, let me just write this down. 1 over the frequency, which is going to be 1 over 20 seconds, or you can say seconds per cycle. Excellent. So let's do another example, shall we? Let's say you got a turning fork that vibrating at 300 hertz is placed in a tank of water. Find the wavelengths in the water and find the wavelengths in the air. All right, here's another example. So we got your frequency is 300 hertz. For part A, your velocity in water equals 1498 meters per second. And for part B, this time your velocity in air is 343 meters per second. And in both cases, we need to find your lambda in water and your lambda in air. So your lambda is going to equal to, again, it'd be V over F. We just solved a while ago. So in our case, it's going to be 1498 divided by 300. So what you got? 5 meters? Almost 5 meters. Yeah, 4.9 something. So if it's 1500, it's 5. So I'm just going to call 5 meters. For this one, what you got? Your lambda in the air is going to equal a v over f, which is 343 divided by the frequency, which is 300. So that's going to actually be close to 1. And you got that half, so I will calculate 0.1. So it'd be 1.1 meters. Awesome. So basically, that's what we defined wave as. And again, so your periodic wave consists of cycles of patterns that are produced over and over again by a source. In the figure, every segment of the slinky vibrates in a simple harmonic motion, provided the end of the slinky is moved in a simple harmonic motion. And the left one is an example of a transverse wave, and this is an example again of longitudinal wave. This is the one we tried to draw in the beginning of the class. Now we also define the amplitude, which is the maximum exertion of the particle, of the medium from the particle's interposition. So basically, it's from your medium line to the end, to the trough, or to the peak of each one. Your wavelength is your horizontal length of one cycle of wave. So each one, that's a wavelength. You can go also from one point to the same point on the other wave, and that should give you the same wavelength. The period is the time required for one cycle to be complete, for the whole one cycle to be complete. That's your period. And the frequency is how many cycles you're doing per second or per time. Again, we just defined this. Your velocity is lambda over t, which is f lambda. So here's a little question over here. You got AM/FM radio, transverse wave consisting of electric and magnetic disturbance traveling at a speed of 3 times 10 to the 8th power meters per second. The station broadcasts AM wave, radio waves, whose frequency is 1230 kilohertz. And now the FM radio wave, whose frequency is 91.9 megahertz. Find the distance between the adjacent crest in each wave. All right, so this is going to be the speed of light, 1230 and 9.1. So let me go ahead. I guess this is called example 1 in my notes. I'm just going to call it the same thing, example 1. So your velocity is 3 times 10 to the 8th power meters per second for the AM. Your frequency is 1230 times 10 to the 3 hertz. You're looking for your wavelength lambda. That means your lambda for this one is going to equal to V over F, which is 3 times 10 to the 8th divided by 1230 times 10 to the 3. So that's going to equal to so I get what? 0.002439. So I'm just gonna go 244 meters. Same thing for the FM. Your frequency in this case is gonna be 91.9 times 10 to the 6 hertz. That means your wavelength, which is your V over your frequency, is going to be 3 times 10 to the 8 divided by 91.9 times 10 to the 6. So this is going to be 3.26 meter. That's what I got. Yeah, that's correct. Now, at the speed at which the wave moves to the right, depends how quick one particle of the string is accelerated upwards, the response of the net pulling force. So let me actually write this down. So the speed of transverse wave or longitudinal wave depends on two things: your elastic properties which is your stored potential energy, and you get your inertial properties, which is, you're talking about your kinetic energy. Now, because it has a speed, that speed is going to be equal to tau over mu, which is tau, that's your tension. Mu, that's called your linear density. And it's going to equal to your mass over your length. So, your velocity is then equal to the F over mu. Mu is called your linear density, which is defined as your mass divided by your length. So let's say we have a question. Let's say we get a transverse wave on a travel on each string of an electric guitar after the string is plucked. The length of each string between its two fixed ends is 0.628 meters, and the mass is 0.208 grams for the highest pitched E string, and 3.32 grams for the lowest pitched E string. Each string is under a tension of 226 newtons. Find the speed of wave on the two strings. So let me go right ahead. So your tension, this is gonna go tension. Your tension I'm just not gonna find it. Your tension T, tau, is gonna be 226 newtons. Now your length for the strings are 0.628 meters. Let me just make sure that's right. 0.6 28 meters, yes. Now your mass for the E string is 2.28, and I'm just gonna count high and low. For the high one is 0.28 and the low is 3.32. So your mass for high, we're gonna be 0.208 times 10 to the negative 3 kilograms. And your mass for the low is 3.32 times 10 to the negative 3 kilograms. That means your V high, I'm just gonna call V high, which is gonna equal to your F over mu, which is again your tension over, actually let me just write this as tension too. Mass divided by length. And this is gonna equal to 226 divided by 0.208. It's not writing good with me. 0.208 times 10 negative 3. That's divided by your 0.628. And your V, let me just clear this down. Your V low, again, your tension over your mu, which is your 226. Actually, let me get a different color for that one. That way we can distinguish between them. Wait, actually, let me just rewrite this whole thing. And green. V low is going to equal to again, your tension over your mu, which is going to be square root of your 226 divided by, this is going to be 3.32 times 10 to the negative 3 divided by 0.628. Let me plug in the first one. So we got almost 826 meters per second for the first one. And 207 meters per second for the second one. Perfect. Now, again, your frequency is your number of cycles per second, right? Now, when you actually use a phone, the sound with a single frequency is called a pure tone. Now, the brain interprets the frequency in terms of subjective quality called pitch. Okay. Now, the sound, we said the sound waves carry energy that can be used to do work. The amount of energy transported per second is called the power of the wave. So the amount of energy transported per second is your power of the wave. Now, the sound intensity is defined as the power that passes perpendicular through a surface divided by the area of that surface. Now, your intensity is going to equal to your power divided by your area. So let's say you got this little example over here. You get 12 times 10 negative 5 watts of sound passed through surface label 1 and 2. The area of these surfaces are 4 meters square and 12 meters square. Determine the sound intensity of each surface. Now you said, so let me go ahead and write the information down. You said the power was 12 times 10 to the negative 5 watts. And your A1 surface is 4 meters square. A2, we said it was 12 meters square. And we want the intensity I1 and I2. Now for this one, your intensity I1 is going to equal to your P over your A1 area, which is going to equal to 12 times 10 to the negative 5 divided by your 4. So 12 divided by 4, that's 3 times 10 to the negative 5 watts per meter square. By the way, your I equals your power divided by the area, which is your watts per meter square. For part 2, your I2, again, is going to equal to your power over your area 2, which is going to equal 12 times 10 to the negative 5 divided by your 12. 12 goes away, so what you're going to have 10 to the negative 5 watts per meter square. Perfect. Now, when you actually hear music or noise, whatever, we have to do something called a decibel. Now, your decibel is a measurement unit used when comparing two sound intensities, because the way in which human hearing kinesics correspond to intensity, it's appropriate to use logarithmic scales for intensity level. Now, your intensity level, which is beta, is going to equal to 10 dBs multiplied by log I over I naught. I naught is your initial or main intensity, which is 1 times 10 to the negative 12 meter squared. So let's do an example, shall we? So you got, if you go to the club and you like to hear a lot of music and all that sound that makes you deaf, let's say audio system 1 produces a sound intensity of 90 dBs and system 2 produces 93 dBs. Determine the ratio of the intensities. So you got 90 and 93. So you know that your beta is going to equal to 10 dBs log. Actually, let me just take this down. I over I naught. So for the first one, for beta 1 is going to equal to 10 log your first intensity over I naught. For beta 2, this is going to equal 10 log your second intensity over I naught. That means if you take the ratio of P2 minus P1, this is going to equal to your 10 log I2 over I naught minus your 10 log I1 over I naught. Now, this is going to equal to, according to logarithms, is going to be 10 log your I2 over I naught over I1 over I naught. Your I naught cancel away. So what you're going to have? You're going to have 10 logs of I2 over I1. And again, this is going to equal to your difference in decibels, which is going to be your 93 minus your 90. So it's going to equal to 3 dBs. That means your 3 dB is going to equal to 10 log I2 over I1, which is the ratio that we're looking for. That means if you actually do a base 10 with this, what you're going to have? 10, not 10. You divide this by 10. So it'd be 0.3. Again, we go to logs of I2 over I1. That means your I2 over I1 is going to equal 10 to the 0.30. So what you get should be 2. Let me just write this down better. Get this out. Yes, that's better. That is better. Okay, perfect. Now the Doppler effect. Hold on, let me go show a video first of the Doppler effect.
If you listen to the sound the horn on a train makes as it passes, you'll notice that the frequency is higher as it approaches and lower as it moves away. We'll now demonstrate this Doppler effect using two small pieces mounted on a swing arm. Here is the sound the speakers emit when stationary. Listen to changes in frequency as the speakers are spun around, alternately approaching and receding from the microphone.
Notice the sound difference when it goes far away from you and it's coming towards you.
Animation shows the sound waves emitted by the speakers when they and the sound waves emitted from the speakers are moving.
Perfect. So let me define some things first for this one. Now I'm going to call the velocity of the source. Let's say you have a source. You have a speaker. You have and this one a train coming towards you that's having a noise coming up, right? So that source velocity, the velocity of your source, we're going to call that Vs. And we can define the velocity of the wave, Vw. We're gonna, I'm just gonna call your source period, and let me just define the source period as Ts, and your source frequency as your Fs. So supposedly we saw that we got a little, that's the train over here going in here. That's your source. And this is the wave that he produced for that sound that we hear. Let's say you're standing, I don't know, let's say you're standing right over here when the train moved to you as in the video. Now, the velocity your velocity, which is going to be what? Distance over your time. That means your distance is going to equal to velocity multiplied by your time. That means your distance from the source, I don't know what brought that up. Your distance from your source to the first wave crest or you can say it's the radius also, is going to equal to the velocity of that wave that's coming out multiplied by the period from that source that you got that wave from. Now looking at both of these, that's going to equal to lambda, which is going to be your distance. Actually, hold on, let me just get a different color because I do not want you all to think that I have this. Yeah, this is better. Yeah, that's actually looks better. Now, on there, you got the train moving. So your source is moving towards you, going to the right. So let me just write this down. Going to the right. So after a while, the source became right over here. And you got distances right over here. So this distance that's going, you got a little train that's moving. That means that train has a speed. So that's the speed of the source multiplied by the period from that source. That means you got this little part right over here. Now, how much this part, right now, this distance is going to equal to, I'm just going to go over here. Now, this distance is going to equal to this big distance, which is your, the wave velocity multiplied by your source period minus your source velocity multiplied minus your source period. Now, we talked about the period of the source, but let's see what the period from the point of view of the observer. So the period from the point of view of the observer is going to equal to what? So the period from the point of the observer is going to equal to what? Now we said the velocity is going to equal to distance over time. The period is basically time. So that's going to have to equal to your distance. Yeah. Divided by your velocity. So the distance is going to be over here for the period from the point of the observer is your VW TS minus VS TW, TS. The velocity of the wave multiplied by the distance or the period of the source minus the velocity of the source minus it multiplied by your period of the source divided by the velocity. Which velocity? The velocity of the wave that's coming towards you. So you can take the period source as common between, so what you get? VW minus VS over VW. So this basically is going to equal to, actually, let me just write it down under it. That means your T naught or TO from the observer point of view is going to equal to TS from the source VW minus VS over VW. Which means the period from the point of view, the frequency from the, let me just write this down, frequency from point of view of observer is going to equal to 1 over T naught, which is going to be 1 over TS VW over VW minus VS. Now, 1 over VS, 1 over TS, that's going to be your source frequency. So this is going to equal to your source frequency multiplied by VW over VW minus VS. Let me actually write it down over here. So F naught is going to equal to Fs V. Again, this is source frequency. This is the observer frequency divided by VW minus VS. Now, actually, let me just write this down better. So this is going to TS VW minus VS over VW. Now, these two equations that we just came in with, this is for your source going to you, observer direction. So this is what the train or whatever that noise is coming towards you. Now, what if, you get the train, you're standing over here, and it passes you? Like the first part of this movie.
If you listen to the sound the horn on a train makes as it passes, you'll notice that the frequency is higher as it approaches.
Now, notice right now he passed me. Okay, it's not going in my direction anymore, it's going away from me.
Lower as it moves away. We'll
So when it goes away from me, let's go ahead. So basically you're right over here. You become right over here. So how do we do this? Well, the distance that is leaving to you for the wave, that's going to equal to what this time? This distance, and I'm going to get a different color. Is going to equal to I'm sorry, hold up. The distance, not from the source moved over here. So this distance, right, all this over here. Actually, let me get a different color. Let me get orange. So the distance is, the train is right over here. It's not over here, it's moved over here. So the distance is all of this in orange. That's the distance that we're talking about, right? So this distance is going to equal to your halfway, which is your VWTS, plus this side, which is VSTS, to get to that point. And if you actually do the algebra for this one, like we just did, you just have the pluses into minuses. So your F naught is going to equal to your FS VW over VW plus VS, and your period from the point of view of the observer is going to equal FS, and you can go do the math if you want, but that's just going to be from positive to negative, where this is going to equal to, not FS, TS for VW plus VS over VW. Now again, let me actually get a different color. This is source moving away from you. And again, you go in for the distance over time. So let's do a little example, shall we? A little fast example. Let's say an example, your VS is 5 meters per second, and your VW is 10 meters per second, and your source period is 1 second per cycle. And your source frequency, that means if this is going to be 1, it's going to be 1 over 1, so it'll be 1 hertz. So that means your frequency naught, which we need to find, is going to equal to, let's say we want to find the frequency from the point of observer going away and coming in. Away and going to. I'm just going to say away and to. So F naught going away is going to equal to your Fs multiplied by 10 over 10 plus 5, which is going to equal to 10 over 15, which is going to be 3 hertz. Now, this is going away. Now, F naught for going 2 is coming towards you. So this is going to be higher pitch. So basically, this is going to be 1, your Fs multiplied by 10 over 10 minus 5. Fs is 1 in both cases. So that'd be 10 over 5. So it'd be 2 hertz. So notice, which makes sense. Notice that when it's coming towards you, it's at 2 hertz. But then when it's coming away from you, it goes down, and this goes down, so it's at 2/3 hertz. Now, that's when your source is moving. Now, let's say you have another example when you're going towards the source of music. Kind of like, I don't know, if you go to Yosemite East to get deaf, and you're over there to the speaker, and the speaker is playing music, and you're close to it. So let's say when you go over there, that's your speaker. And this is you right over here. And this is the first crest wave. Now, this time you are the one who's moving. This is stay still. Stay still. Now, this time you're moving, and you move right over here. Now, the distance that goes in from a speaker to you is that wave speed multiplied by the period from your point of view. Now, you're the object in this case, so when you're actually moving, this is going to be your moving speed multiplied by the period from your observer point of view. That means that for default radius, this is going to equal to your VWT naught plus V naught T naught. And again, all of this is going to have to equal to your wavelength lambda. Actually, let me just do it a little better. Yeah, that's a little bit better. So let me actually write this down. So T naught is the time it takes until a wave crest hits you right over here. And your V naught, that's your speed of observer. And we said the lambda is going to equal to your VWT naught plus your V naught T naught. And that's what we just had. Taking T, the period of the observer, from both, what you get? VW plus V naught. That means T naught equals lambda over VW plus V naught. But, and a big but, again, your velocity is distance over time, which is your lambda over your period. That means your wave velocity is the lambda for the wave from the source to your period from the source. That means your lambda is going to equal to your wave velocity multiplied by your period from your source, Ts. So we can go ahead and substitute. Actually, let me get black. This lambda over here with this lambda over here. because we want to have, here's the thing. So this is observer, but this is source, right? So we need to have it as a source. So T naught is going to equal to your VWTS over VW plus V naught. That means your frequency for the observer, which is 1 over T naught, is going to equal to VW plus V naught over VW. Now, all of that is going to be multiplied by 1 over TS, which is, again, this is going to be your source frequency. So F naught is going to equal to your source frequency multiplied by your VW plus V naught over your VW. So this is for going towards the source. And same thing, if you actually were behind the speaker, going away from it. Let's say you're walking, and then you go behind the speaker, away from it, this side, right? So you're just gonna move the positive to negative. So your F naught is gonna be Fs VW minus V naught over VW. This one is going away from speaker. Probably you got tired by the end of the night from hearing loud music at Semites and decided to leave. So you can actually combine two formulas and having a general formula. So your general formula, your F naught is going to equal to Fs 1 plus, well, if you actually solve it, you can go 1 plus V naught over VW over 1 minus V source over V naught. Oh, I'm sorry, this is VW. And then if you're going the other way, you just change the sign. So the W effect is the change in frequency or pitch of the sound detected by the observer because the sound source and the observer have different velocities with respect to medium of sound and propagation. Now, actually, this is one of the things we explained. We just explained this, how we got this. And, oh, one thing before I forget. In your book, it reaches the VW, it actually calls it also V naught. So as both of them are the same, if you want to follow your book, which is this one over here. So again, we just derived these equations in here. Here's a little example. You can go ahead and start doing it, pause the video and put it in and plug in the numbers and see if you can get it. Here's the answers over here. And this is your general formula that we had, that we actually derived by plugging both of them in. We just went inside of it in a little detail for the whole thing. And that should do for our chapter 16 for Physics 102. If you have any questions, just email me at apunaem@uah.edu, or you can call me at 256-348-1480. Have a nice day.